So this is probably the most interesting and important part of sensors, right? You have almost everybody deals with a motor with an encoder because you have to do something useful as position control. So an encoder will do that. So an encoder is a device which measures the angular position, and it does using an emitter detector pair, something we've done in the first part of today. Now, the difference between an encoder and a potentiometer is that potentiometer produces an analog signal, but encoder produces a digital output, which is nice because then it's much easier to interface this with a computer. We talk about two types of encoders. There's an incremental encoder, and then there is an absolute encoder. An incremental encoder measures relative change in position, while an absolute encoder measures absolute position. Okay. Because it produces absolute position, it requires more circuitry. It is more expensive than incremental encoder. However, if you want to just measure the speed using finite difference, then you can just buy an incremental encoder. Absolute encoder is not needed. So as I said, there's a shaft. It will have a special coded disk, as I've shown here. It has black lines. There will be a light emitter, and this light emitter passes through this specially coded disk. This is received by a light detector, and clearly based on whether the light passes or not, because of this disk has black lines or white or transparent lines, you'll either have an output of zeros and ones, and that's how it converts the light data into bits, zeros and ones. Okay, so let's take a closer look at this. Okay, let's consider an encoder with just one disk. This is this A. It has black and white lines, or transparent and opaque lines. Okay, so clearly, let's assume that there's a code, and when it is dark, it's 1. It's white, it's 0. Now, what is done here is it has certain number of slots. Okay. So let's say there are 30 slots. So if you have 30 slots, then we know that it'll either be zeros. If there are 30 slots, we know that each slot would be 36 divided by 30 is 12 degrees. So each time it goes from black to white or opaque or 1 or 0, we sweep 12 degrees. So once we know that it is 12 degrees per 1 and 0, we can then figure out what is the angle turn. So for example, for the same example, 30 slots, if we note 14 highs, 14 ones, 14 such peaks, then we can compute the angle turned as a number 36 divided by 30, which is 12, times 14, which is 168. So it says turn 168 degrees. So all you need to do for something like this to measure the angle is you just need to count. You just need to count. That's it. There's something you need prior, which is you need to know the number of slots, but you only need to count in order to figure out the angle turn, which is really nice. It's very simple to count than to do anything more complicated. Now, there's a problem with a single track. What is a single track? Just one track. It can only give you the angle turned. It cannot give you direction. It cannot provide direction. But for any sensitive useful, we also need the direction. So what is done in that case is you need at least two. You at least need two patterns. You need A and B, okay? And they're the same thing. They're the same strips, but they have there are two strips. Now, what is done here is these strips are, remember, there's on a disk. Okay, so let's say that the inner one is B. This is B. This is A, and so they'll have their own black and white, and so on. Right? That's what I'm showing here, but I'm just showing it in a linear fashion. Now, the way they are printed is that there is some overlap, overlap. So if you think of this as one unit, black and white, you can divide it into two parts. 1, 2, 3, 4. The overlap here is 1/4. So that's why it's called a 1/4 cycle out of phase. That's why if you hear of encoders, you hear the word quadrature, and that's because of this 1/4 cycle out of phase. Okay, all of them will have this 1/4 cycle out of phase. Okay, now with that overlap, just that simple A and B, the way they're shown, we can write ones and zeros. So remember that black is 1. We write this down. Okay, so black is 1, 1, 0, 0. Right? The same thing is written here, 1, 1, 0, 0. And then we have, this is 0, 1, 1, 0. So 0, 1, 1, 0. So I just copy pasted what I see here right over here. Okay, this is 1 unit, and I just copy pasted the same unit again. The same thing is repeated again. Okay. Now let's, as we said, now we are using this to measure the direction. So this is how it works. So I've written down 2 of these units again. Same thing written down. Okay. Let's assume that we start from 0, 0. Okay, just arbitrary number. You can choose anything. Let's just 0, 0 is easier. So let's assume that this way is clockwise, this is counterclockwise. That really depends on how it is mounted, but let's assume that that's true. So what I'm doing here is when I write CCW, I'm taking this and I'm writing these numbers from 0, 0. So starting with 0, 0, I wrote 1, 1, 0, 0, 1, 1, 0. I did not write the last 0. And then I have 0, 1, 1, 0. Okay. Similarly, for clockwise, going this way, I wrote down 0, 0. This was my first. And then I wrote 0, 1, 1, 0, 1, 1. This is for A. And 1, 1, 0 for B. So this is just what you have over here is just rewriting of what I see there. Okay. This I showed as a timing diagram. So 0, 1, 1, 0, 0, 1, and same thing for clockwise. Okay. Now, as I said, we are trying to figure out the direction of motion. Okay, so what we have to do is we need to discern a pattern. Here you can see that starting with 0, 0, we go 0, 1. So here, for counterclockwise, A happens to be 1 first. So A leads B because it went to 1, 0. Well, if you compare it with here, we have 0, 0, same thing, same start, but here B has come out to be 1 before A. So all you need to do in order to sense the direction is that, note this. So here, for counterclockwise, A leads B, A hits 1 before B, and for clockwise, B hits 1 before 0. So just noting that fact, you can figure out the direction. That's all to it, to measure the direction, just the leading and lagging. Okay. Okay, now this is a little bit more complicated than that. Now that you know, you have a general idea of how that works. The way this goes is this is how it is implemented in hardware. There are 3 resolutions. Resolution is how with the same pattern, same code, A and B, what is the smallest change in angle can you detect? That really depends on the kind of counting architecture you use. And we're going to use the flip-flops counting architecture. So there's 1x, 2x, and 4x. Okay, the way this 1x, 2x, 4x works is basically what type of flip-flop we use. Okay, so let me backtrack here. First of all, this A and B is the same as what I've shown here. There's no difference. Okay, I just took the same thing, just the same thing, and I copy pasted this. There's nothing new there. Okay. Now, as I said, there's 1x, 2x, 4x. What these are is 1x uses negative edge of A or B. The keyword is or B. So here, for example, if A did the negative edge, we use a negative edge trigger flip-flop to measure, to sort of count. Okay. So here, let's say that we use A. We could use B, but let's say we use A. So when you say 1x, you'll see that it is triggered when this hits negative edge. Similarly, negative edge, this gets triggered. Same for here, negative edge, trigger. Okay. if you want to use the 2x resolution, you'll trigger in the negative edge of A and B. Okay, so you'll use both edges. So let's use a different color here. So negative edge of this is the negative edge of B, negative edge of A. So this one is triggered by, here you can see negative edge of B, negative edge of A, negative edge of B, negative edge of A. And same for here. Negative edge, missing one on the right side. And then the last one, 4x, is triggered on the positive and negative edge of A and B. So there you'll see that it has many more spikes. So these come from this edge, this edge, this edge, this edge, this edge, this edge. So you see more spikes. Anyway, so this is 4x. That is, here you're just going to count these edges. So if you count 1, 2, 3, 4, 5, 6 in one cycle, you only count 2 here and you count only 1 here. So it's 1, 2, and in this case, sorry, it's in 1 unit. So this is 1 unit. In 1 unit, you have 1x, 1 trigger, 2 triggers, and you have 4 triggers. This 4 is the 4x here. This 2 is the 2x, 1x. So you can, for this much rotation, you can count, you have a resolution of 1, 2, and 4. Okay, so that's why they have different resolution. Now, how to use this to determine the direction? I'm just going to show it for 1x. So for 1x, for this is clockwise. So when A goes down, B equals 0. So A goes down, so it's shown in yellow here. When A goes down, B equals 0. And here, when A goes down, B equals 1. So B is 0, B is 1. Put a different color here. So this is 0, this is 1. Okay. On the negative edge, one of them, the counterclockwise goes to 0, and clockwise goes to 0, is B0. Here it's 1. That's all is needed. Just this bit of information. For the same trigger, for the negative trigger, B is 0 and 1. If it is 0, then it's clockwise, B equals counterclockwise. Okay, and that's all which is used to figure out the direction. All you need is this one piece of information. Okay, one last thing, and we are done. What I have over here is very similar to what I said. This is like number of slots. You can find the resolution, and I have an example, and I will not get into the details. As I said, this is a low-cost encoder. The disadvantage is that it can only sense the change in position. It cannot give an absolute position. But however, there are these encoders called a Z with a Z channel, and third channel is to zero the encoder. And sometimes you'll see a Z in the spec sheet. That means that's an incremental encoder with the capability to start it at a given position, a 0 position. Okay, this is the last thing, and we're done. An absolute encoder provides absolute position. So you'll remember its 0 position. It has 2n levels, where n is n tracks. Okay, if there are n tracks, then 2n levels, and the resolution is going to be 360 divided by 2n. Okay, so here is an example of n equals 4. This is what the track will look like. Here is an example of a section of the track. Okay, so this is basically what is shown over here is the timing diagram. Just anything white is 0, anything black is 1. This is for bit 3. For bit 2, same thing is done, and so on. So what you can do is, based on the range, since this is 4 degree, this has 4 bits, or n equals 4. It will have 16 levels. That means it can only measure 360 divided by 16. The 22 increment 5, so 22.5, next 22.5, and so on. So each of these numbers from 0 to 15 can be mapped to an angle, as shown here. And then if you look at this gray code, which is this track, then you can write a binary code based on the bits. So for example, we have here, this is 0, 0, 0, 0, that's showing up here. It's B0 is 1, as you can see. This is B0, it's 1. And you just can write binary numbers based on the track over here. But this does not really correspond to 0, 1, 2, 3, 4, 5, 6, 15. You really want to interpret this as a number from 0 all the way to 15, which is, this is a binary equivalent of the decimal codes, 0 all the way to 15. So what is done is, you basically create a logic gate which maps the gray code to the binary code. And you can use sum of square product of sums to figure this out. This is the logic. Okay, and that's it. You basically use this kind of logic to convert the angles to a number, or these levels. And these levels, this, for example, if it's 6, the range is somewhere here. If you clearly, this is not a good range, 22.5 is very inaccurate. So in order to increase the kind of resolution, what you need to do is you need to use more number of bits. You will usually see 12-bit encoders or 14-bit encoders, which means that it has 2 raised to 12 levels or 2 raised to 14 levels. The bigger the number, the higher is the resolution, the finer you can measure. And that's all to it. The only thing I want to mention in passing is that all these encoders are based on counting, as I showed you earlier, and these counts go really high. So here is an example. This example shows that the counts goes to 66,000 for a 1,000 RPM. A computer cannot keep track of 66,000 counts. So what you do is you have a special counter called, in this case, LS7166, which actually is a 24-bit counter. It can keep track of counts. And you'd use a counter like this, a specialized circuitry, in order to keep track of count, which will then give you the angles for a higher resolution encoder.